No, I'm just kidding. All right, thank you guys so much for joining us for our second talk. Proud to introduce Christoph Neumann, the founder of Hypersignal. Again, what we used a couple weeks or a couple months ago. I will turn it over to you. Thank you so much.
Hi, I'm happy to be speaking instead of just attending. It's a lot of fun. Like Dan said, I'm Christoph Neumann or Neumann. If you want to be German, authentically German, then Christoph Neumann. But or if you call me Christoph Neumann, I'll respond. And yes, I'm the founder of Hypersignal and AppSauce. And so my background is in software engineering as a developer, and I created a software consultancy many years ago now, and we create custom solutions for automated video production. And either that's with data integrations or video integrations, but almost always both, right? Data and video. And then I have a product that I developed with my company called Hypersignal, which is really all about taking WebRTC and the browser to an interesting place. So it's used for contribution from anywhere. And so we'll circle back. We'll talk a little bit more about Hypersignal at the end. But the goal of this talk is to talk about WebRTC, how it's used in live production, and then some examples, and then maybe how, my take on it. Okay, so just a little bit of background on me. Way back in the dawn of the 2000s, I was working with video. I've always had a fascination with video. I've always been a programmer, a developer. I've always found video interesting. And so I've been a video enthusiast for years, and then later on became a video professional. And I had a stint as a CS researcher, got a master's in computer science at Oregon State, decided I liked industry better, no offense, academia, came back in industry, got involved in manufacturing and automation, worked on some pretty big scale projects, ended up getting involved in real-time data and monitoring because of manufacturing, and just really fell in love with real-time things, real-time data, real-time visualization, real-time monitoring, all that. I then decided to become independent. Mobile was huge, went into mobile apps for a bit, and did that, got a little bored with mobile, and then in 2015, I fell into live video production, and I thought this was amazing, because this is the confluence of real-time and manufacturing together, and video, all in one, right? Because you are essentially manufacturing something live, and fell in love with that. So I've been doing live video production since then. I have worked with a lot of different brands and projects and so on and so forth. So I'm available to hire. Plug, if you want to hire me, my info will be at the end. But before we dive into WebRTC, let's talk about why do we care about real time? You know? First there's recorded, and then there was live, and now there's real time. Like, why do we care about real time? I know you thought this was going to be a talk on WebRTC, and it's going to be a talk on philosophy before it's a talk on WebRTC. But why do we care about real time? Why isn't live good enough? What do you think? Why isn't live good enough? Why do we care about real time? Latency. Yeah, latency, interaction. Yeah. I like these answers. Humanity. Okay, elaborate.
Because it's like, you have a Zoom call with somebody and there's even a fraction of delay, it doesn't feel like you're there having a real conversation versus me being at the bar and stuttering over my beer.
Yeah.
Latency in real life, but at least you're there to see it with me.
Yeah. I like this, humanity, right? So when you have latency and interruption and jitter and stutter and dropouts and all that, when you're trying to talk to somebody, it just really hurts the humanness of that interaction, right? So real time is because we want to erase distance. We want to be together without being together. That's really what real time is about. We want to get rid of distance, and if we can take away the effects of distance, then we can feel like we're in the same place without actually being in the same place, and that changes everything. So that's really what real time is about. It's not just about being faster and, oh, we got our broadcast from 7 seconds of latency to 2 seconds of latency to half a second. It is about feeling like we are in the same place, right, at the end of the day. And so if we can get rid of distance, then we can have true interactivity, right? I like it, but it's a human thing. So real time, if we can execute it, will erases that distance. That's huge. So in order to be able to erase distance, we have to understand what the barriers are that are imposed by distance, right? Just being connected at all. If we can't get connected, well, there's no point. If we are connected, but the other person sounds like a robot, or we can't see them, or all the above, well, that's an issue. If it looks great, and you talk, and then I have to wait, and then I talk, and you talk, that's not great either. If it's a great experience, but only 2 people in the world can do it, who cares, right? We need lots of people to be able to do it. If hundreds of people can do it, but it's super expensive, well, you can only do so often, right? You can only be together so often. And if it's a great experience and all that, but there's no privacy, then that's going to limit the amount of use. So these are the big barriers that are imposed by distance, right? We lose privacy. It costs a lot of money. Not everybody can be there. There can be a lot of delay. The quality's terrible. We can't even get connected in the first place. So all of these are hard problems. So first, you have to know your enemy. The enemy to real time, the enemy to latency. Well, our enemy and our friend, as so often is the case, is the internet. The internet is the enemy, but the internet is a way. So welcome to the jungle. On the internet, we have latency, we have jitter, we have packet reordering, we have packet loss, we have congestion, we have limited bandwidth, we have firewalls, we have NAT, we have connection instability, we have untrusted federation of networks. We have all this stuff happening at the same time. And somehow, which I find fascinating, back to the existential questions, somehow this is the way we have managed to get the world connected. There have been a lot of ways to do this in a more beautiful, less chaotic, less top-down engineered way, but the way that keeps winning is the internet, right? This kind of amalgamation of parts all thrown together. So the internet is our way, but these are the problems that we have to deal with. So we have all these little packets that get sent from one little network to another. We're on a network here, and this network here is sending us to another network, and another network, and another network, and another network. And it's all buffered up and passed along. Ran out of buffer? Well, let's throw it away, right? Too busy? Well, we'll hang on to it a little bit, but if it's still too busy, we'll send it that way this time instead of the other way, right? Did it get there? I don't know. It's not my problem, right? It's your problem. It's the problem of the endpoints. So the internet is a challenging place. So TCP is nice because it hides a lot of that from the end applications, right? It handles retry, it handles all that. That's great. All you have to do with TCP is wait. Sometimes you have to wait for a long time, right? The default timeout in TCP, who knows what the default timeout in TCP is? It's like 2 minutes, right? So you just, if you can wait. But what if you can't wait? Right? Latency is a big issue to that. So what if you can't wait? Well, sometimes when you're dealing with a jungle, you have to get out the machete, right? And you got to hack on the jungle a little. And this machete that we're going to get out, it's called Datagram is the name of this machete. So WebRTC is built on datagrams. So when I first started with WebRTC, so a little bit of history on me and WebRTC is I have used WebRTC. I was aware of WebRTC, but I became a WebRTC developer in late 2020 and early 2021. as the world is in upheaval and everything is moving, I went from traveling about a third of the year going to live events to not traveling at all. I was involved in a project where we had worked on for 2 years to take an esports show on the road, and it was going to be a big deal. We were going to be concurrently every week in 3 different places around the world, Europe, North America, and Asia. And we'd spent 2 years of engineering effort and time and thinking and planning to take this esports on the road. And then we were asked to pivot in 2 weeks and make it a cloud-based production instead, because that was in 2020. We'd been on the road for a couple of months, and boom, hard pivot. So all of a sudden, I found myself at home. I found myself pivoting to the cloud. I found myself very interested in telecommunications, and I found myself interested in WebRTC. And I'm like, oh, what is this protocol, WebRTC? And I discovered that WebRTC is not a protocol. It is a tech cocktail. It is a full concoction of tech standards that systematically attack the internet jungle. So it's not a protocol, it's a whole bunch of things, all wrapped up together. And we're gonna see some familiar friends in this tech cocktail, but WebRTC itself is not a protocol. So if you're unfamiliar with WebRTC like I was, I thought, oh, well, let me learn this protocol. WebRTC attacks our enemies of being in real time, being there together. And it does that with UDP and ICE and stun and turn and RTCP and NACS and jitter buffers and bandwidth estimation and DTLS and SRTP and adaptive bit rates and round trip time measurements and picture loss indicators and out of band signaling and SDP. Oh my, right? So WebRTC is all of these and more. Actually, this isn't even everything. This is just a piece of what WebRTC is. I don't know. Okay, so how many people here feel like you know the innards of WebRTC? Okay, so a third of the room maybe, right? How many people feel like you kind of get WebRTC, sort of get the stack, maybe not the innards, but you're kind of there? Okay, a couple more people. So WebRTC is a few different phases. So you can think of it as a few different key pieces. So WebRTC is session-based over UDP. It's not multicast. It uses SDPs to be able to establish that. So that's the session description protocol. I had a little cheat sheet of all the acronyms, and I forgot it at home. So I'm going off my memory here. So it uses the session description protocol, which is ASCII protocol, that tells you, like, here's the media I can send, and here's the media I can receive, and here's how many channels, and so on and so forth. You exchange that somehow. WebRTC doesn't say. It's up to you. And then once you have that information about ports and protocols and codecs and all that, then, well, not protocol, ports and codecs and all that, then you trade that, and it begins to try to establish a session. Now, what I think is funny is first there was stun. And then stun was all about NAT traversal and punching through NATs. And stun didn't quite get there most of the time. So then they added turn. Turn is for relaying around. And then even still, so then they added ICE, which is like even more tools. So it's just this giant grab bag of tools for NAT traversal, stun, ICE, whatever. We'll get into detail. Then after we get this session, great, we can set up a DTLS session. So DTLS is just simply TLS, but D is for datagram. So it's the UDP version of TLS, which is like SSL, which we're all familiar with. And then we set that up. We exchange session encryption keys over this new encrypted DTLS session. And we use those session encryption keys for secure RTP. So at kind of the workhorse of WebRTC, working this backwards, after you do all this work to find out about each other, and get connected and trade keys is RTP. So WebRTC is RTP plus more. And it's RTP plus specific RTP standards. Okay, so here is how WebRTC attacks the internet jungle. It tames the internet jungle of NATs and firewalls by using ICE and stun to get all of the IPs that it knows about. And it looks at your browser or other implementations, look at what IPs are actually bound to this machine, what IPs, it reaches out to a stun server and says, hey, what are my public internet IPs, and so on and so forth. And then it does this crazy thing. It exchanges those, and it tries them all at the same time, in parallel. And it says, okay, I'm going to try to connect. I'm going to try to connect to all of them at once and see which one works. And that helps it get around NATs. It helps it punch holes through NATs, figure out if NATs exist. When that doesn't work, you can also have a relay, which is a turn server, so that you just say, you know what, I can't connect directly. I'm just going to relay through a server on the internet instead. And that isn't necessarily enabled by default. You have to set that up because now you're on the hook for all the bandwidth going through that turn server. So there's infrastructure providers and so on and so forth. So that's how it attacks the NATs and firewalls aspect. It attacks the untrusted nature of the internet by building in encryption and making it mandatory. So there isn't unencrypted WebRTC. There's only encrypted WebRTC. It has to be SRTP. It has to be DTLS. So it's built in. So if it's a WebRTC connection, you can know that it's encrypted. It attacks packet loss because part of RTP is the RTCP response packets, right? They're out of band, so you have one port for exchanging RTP, and you have a separate port for exchanging the RTCP, the real-time control protocol, and that provides feedback so that you can understand when packets go missing, what the jitter is, what the round trip time is, and so on and so forth. That feedback can be specific kinds of messages, and one of those says, hey, can you please send me a full keyframe because I just need to reset the decoder. Like, it was so bad, we lost so much stuff, the decoder has no idea what state it's in. Send me a keyframe, let's start over. Or if you drop some packets along the way, it will send a negative acknowledgement which says, hey, resend me these packets, or resend me this range. They're all sequentially numbered. I missed some, so fill in the gap. It attacks congestion, and this is the really tricky part. It tries to attack it as best it can. Using that feedback, it can estimate how much bandwidth is available. And the bandwidth estimate is really more of like, I tried it and it worked, so at least that much bandwidth is available. It's not an absolute sense. This isn't like running a speed test and getting the upper threshold. It's sort of an attempt to send more and more and more and more and more and figure out when it doesn't work, right? That's what the bandwidth estimation is. And then in the most sophisticated, there's a feedback loop between the RTP layer and the encoder itself, and it will dynamically decrease the bit rate. So we'll use an adaptive bit rate. Because in the end, when we're talking about maintaining a human connection or feeling like we're there, we're trying to control machinery or we're trying to control something without being there, it's super important that it's real time more than it is perfect quality in many cases. So we'll just dial down the quality. In order to handle jitter and reordering and all that, implementations use a standard jitter buffer. That jitter buffer in some is configurable, so you can add more latency to handle more packet loss and more jitter and more reordering. And like Chrome, for example, the Chromium implementation of WebRTC allows you to have what they call playout delay because it uses that jitter buffer as kind of the buffer also for the decoder. So you could just add more delay and get more resiliency. Kind of like SRT, you add more delay. And it overall tries to manage latency by tuning these buffers as small as possible, using that round trip time estimate to kind of optimize the retransmits and so on and so forth. So that's sort of a quick overview of WebRTC as a technology. So we have all these standards, and we're attacking all of these problems using all these different pieces together. Not every implementation has every piece, but there's a mandatory minimum to call yourself WebRTC. You have to have SDP for your sessions. You have to have DTLS for the actual session connection. You have to use SRTP, and there's some minimum codecs that you have to support. So you have to support VP8, you have to support Opus Audio, and I can't remember if H.264, VP9 is, but H.264, yeah. Yeah. And the frustrating thing in this ecosystem is depending on which device you're using, it may support others. The practical limiting factor that I've run into many, many times is Chrome supports Opus. So, and there's all kinds of patents and issues around AAC and definitely AC3 and Dolby Audio in general. And so it doesn't support those. So why WebRTC? So why would you want to use WebRTC as part of your overall production? So like I said, I'm not on the distribution side. I'm on the production side generally. So it's fun to come to this meetup specifically because there's a lot of talks about distribution. We were just having a talk about distribution. It's a great talk, right? And it's ad placement. It's a distribution problem. So on the production side, you have different problems than on the distribution side. Usually on the production side, you just throw more bandwidth at it. On the distribution side, it'd be cost prohibitive, right? So on the production side, you need extremely high quality because you're not going to get it back, right? And so I primarily work on the production side. So WebRTC has on the production side, can fit in nicely. It fits in nicely when you need interactivity. If you do need peer-to-peer, it fits in nicely because it can do peer-to-peer. Because it's so good at setting up sessions, it can set up sessions in a very ad hoc way. It's extremely ad hoc because its background is telecommunications, right? So it's all about communications. It's great for using existing devices. Every web browser supports WebRTC. Even old versions of web browsers support WebRTC. And it's been around for a long time, so you can use existing devices if you need to. You don't need to buy another box and hook it up to another monitor often. You have something that will do it. It's great for unknown network conditions because it's adaptive. And if you cannot control infrastructure, WebRTC is wonderful, right? So if you need to bring in a remote guest into your talk show and they're at home, you don't control a whole bunch of that infrastructure. WebRTC is wonderful for this problem. If you need localized traffic, because of the way ICE works, it will find all the IPs. So if you are on a network that allows clients to communicate with each other on that network, WebRTC can often set up a session that never leaves the LAN, which is really nice, right, in some cases. And then, I mentioned it's ad hoc. So if it's totally ad hoc, it's wonderful for that. In some cases, you're in this hybrid where you do control part of the infrastructure. You can put a media server up there or a relay out there, and you can control part of the infrastructure. And then that simplifies some things. You don't need peer-to-peer for WebRTC. You will add some latency by going through that server, but often it isn't very much. Most of the latency in these connections is getting out of somewhere and then getting back into a different venue. Right? The backbones don't have a lot of latency. It's the home DSL lines and, the Wi-Fi, right? That's where the latency comes. And with that server, there's less obstacles to connecting because you don't have to worry as much about firewalls and NAT traversal, but you still often do because things can originate from inside the protective shell and just go to the server. The server can be public. It is less adaptive, though, because you don't get all this feedback from a direct peer. And because with WebRTC, it can actually tune the connection between two peers. And so we'll take a look at that. And a couple standards emerged in the last few years to make this simpler. Because if we go back to WebRTC, does not care how you exchange the SDPs. It does not care how you exchange the session setup information. That's been a limiting factor because there isn't a standard. And so in the last couple of years, standards have emerged that use HTTP as the way. So you get your SDP, you post it to an HTTP server, and its reply is the answer. So you post your offer, and you get your answer to HTTP. It's kind of fun because the server doesn't necessarily have to answer it. The server can just broker it. And so there's implementations where you're actually setting up two peer-to-peer clients through that HTTP connection because it's talking to both of them. But it's a simpler way. It's a nice standard way. So because we've seen WIP for pushing a stream up and WEP for pulling a stream down emerge, we've seen this get built into a lot of tools. You may not want to use WebRTC if you care about delivering every frame from point A to point B. Not your best choice, unless you can totally control the network or you have implementations that let you add a ton of latency. If you need a stable fixed latency, so like an SRT or like a broadcast production workflow. So I'm working on a project for live sports. That project, we're getting feeds out of stadiums into the cloud. We're hooked into the switcher. The switcher, we get GPI from the switcher, right? And so we're timing wipes and stingers to match that GPI signal. Well, we don't want the latency between us and the stadium changing, right? We want to lock that in. WebRTC, not great for that, right? It's always trying to kind of dial in. A lot of implementations are trying to dial in. Well, actually, if it slows down, it will kind of spread out the samples, and then it will speed up the samples to catch up, right? So it actually changes time a little bit in order to catch up, right? Because it's trying to be on the edge. The Chrome implementation does that. If you need to integrate with traditional broadcast gear, not great. If you need to use patent-encumbered codecs, right? These are not what we call open internet standards. They might be standards. They're just not open internet standards. You're going to get frustrated with WebRTC. And if you need an MPEG-TS style workflow, right? WebRTC is based on RDP profiles, not the RDP that encapsulates MPEG-TS. And so you're going to find yourself digital TV and all that very frustrated with WebRTC. So just kind of briefly, some comparisons. So versus RTP, well, WebRTC is RTP, but it's RTP plus more. SMPTE 2110 is RTP, but it's RTP plus more, right? It's specific RTP profiles and standards and a whole constellation of standards around RTP. RTMP. So RTMP just had a whole new lease on life in the last year or so with enhanced RTP. So now RTMP can encapsulate H.265 and more modern codecs. RTMP is TCP-based. RTMP is super simple. There's a reason why it's the most popular contribution protocol for all streaming platforms, because you just start sending it to the server, TCP handles it. You're going to find over time that buffer's going to grow. I've used RTMP a lot. That buffer grows over time. But every frame is going to get there unless your internet totally dies. It's just really simple, right? It's not real time. That's the challenge. And in one of my projects right now, we're using RTP on the LAN. And even on the LAN, these buffers grow. And so we have to reset our streams periodically. Works really well on the LAN, but the buffers still grow. What about MPEG-TS over UDP? That's UDP, right? That's real time. This is like the classic for digital television, right? And digital television distribution systems, like on an infrastructure. Well, that doesn't give you a whole lot of reliability. No retransmits. That's typically multicast. WebRTC is session-based, so it's UDP. SRT. SRT is great. It's UDP. SRT is MPEG-TS encapsulating. so it's MPEG-TS inside of the SRT, you get a fixed latency. And if you really don't want to lose any frames, then you have to set that, practically speaking, you have to set that latency to several seconds over the internet. Well, that is the total opposite. If it's okay to drop frames, then you can try to dial your SRT or your ZigZag down, but you still can't get it as far down as WebRTC implementations. And MPEG-TS is a totally different beast than RTP. That's another talk. We can do a different day. And then RIST is also RTP-based. So RIST is kind of cool because RIST reminds me of taking some of these features that are in WebRTC, such as retransmits, and some of the features that are in SRT, like bonding, and then stacking them on an RTP platform that's really designed for internet transmission, whereas SMPTE 2110 is not so much designed for an open internet transmission. So RIST is kind of like the production video backbone option that's emerging. I find it really interesting. But once again, RIST is supported by very few things in the consumer space, basically nothing. And you know, it's a standard that's emerging over time. And then HLS and MPEG-Dash, I want to mention those. Those aren't really contribution protocols, although they have been used for contribution. And they're chunked protocols, so they have you have low latency HLS and low latency versions of MPEG-Dash, where we just make the chunks really smaller, but we still, and because we're chunking it and we're delivering all those chunks in parallel, we're trying to deal with internet latency and so on, but you're never going to get the latency down to what WebRTC does. So that's just kind of a quick comparison between that and all these different contribution protocols. So you really want to use WebRTC in production if you have remote operation of something. So you want a real-time preview from a remote system, and this is becoming very common. And what's interesting is people will say, oh, well, you can use desktop sharing for remote operation. That is true. Well, a lot of desktops, the best desktop sharing clients use WebRTC under the hood in order to do that. So you might be using WebRTC without realizing it. If you want a remote guest on a talk show or things like that, WebRTC is perfect. In that case, it's perfect because it just works. It's the ad hocness, right? Because WebRTC is systematically attacking all of these enemies of distance, right? All these enemies of being together, really. It's great for this. If you have a bunch of presenters in different places or multi-site events, WebRTC is great, right? Because you don't need every frame, but you do need it to be interactive. You want to be able to talk. If you want to have a real-time preview for a delayed feed, so the operators or the control center or the people in charge, they want to see what's actually happening right now. That isn't what's going to walk out the door. You want your high res to walk out the door, your high res production flow to walk out the door, but you need to know in advance what's going to happen. WebRTC is perfect for that. In some cases, VIP feeds, right? Executives or people who pay a premium, they get that low latency feed. Or in general, if you just need any kind of audience presenter or presenter to presenter interaction, WebRTC is great for that. So the reality is that WebRTC isn't your whole workflow. It's part of a larger workflow for production. And as more live video production is moving to an amalgamation of on-site resources and cloud resources, WebRTC starts popping up and finding a place in serious production workflows. So let's look at a couple of examples. So simple example, Twitch enabled support for WebRTC contribution. This is great because Twitch is all about streamers, and streamers are all about interacting with their audience. And by allowing for WebRTC contribution, they lower the amount of latency between them and their audience, and they can interact better with their audience. So obviously there's still a whole, as you all know, there's a whole infrastructure catching that contribution and doing all the encodings that are needed to deliver different varying bit rates and so on and so forth. But we're able to squeeze out a few seconds of latency on the contribution side using WebRTC, which is nice. This is another example in pictures. So here's an example of a remote presenter. she was in Sydney, Australia, and this is Wimbledon. And so you have a couple of hosts that are chatting with her. So here's the funny thing. She didn't have any power in her home, and she didn't have any internet, which is kind of wild. So she's on her laptop on a cell phone hotspot being interviewed for Wimbledon. That's pretty cool, right? Like, can you think of any other production scenario where somebody could just fire up their laptop and fire up their cell phone she's a reporter, so she has some experience with video tech, but she's being interviewed. In this case, this was with my product, so that's why I have a screenshot of this. And yeah, she's being interviewed on what her take is for Wimbledon. Here's another example. So here we have a stage. I don't have a shot with thousands of people that are in the live event audience, but another example where you have a live event. This is for Snowflake, a big data platform. And they did a contest to give $1 million business plan prize, right? So a whole bunch of people submitted, hundreds of people submitted business plans. They winnowed it down to the 3 finalists. And they had a problem. One of the 3 finalists was in India. And the way they always do this contest is they bring all the finalists on stage at their big convention every year, and they interview them on stage and ask them all the hard questions. And so these people in the chairs, those are the judges, and they're different executives in Snowflake company, right? And they ask them all the hard questions. But some of the finalists were in India. And they couldn't get into the U.S. as a combination of visa and COVID restrictions and all this. And so they brought them in using WebRTC to the big screen, right? Once again, this was with my product. That's why I have a screenshot of it. But they were able to bring them in virtually. Clearly, being there is better. We still have much higher fidelity of being there. But they were able to do that. The best part is that's the team that won the $1 million prize, right? So imagine like what disadvantage you would be at if it just keeps cutting out and dropping, right? So as we erase distance by attacking the barriers that are imposed by distance, we can begin to have more of these experiences. So the way this works is you have WebRTC between the person and the control room or some kind of on-site control room. And then once it hits the venue, it's all baseband. Okay, so here's another example of a workflow. If you've never seen this before, you're putting graphics on something, right? So you have different cameras and you're putting graphics on top of that. And so in this case, this is a multi-view, for example. And so the way that works is for a live sports scenario. So I've worked with live sports, and you have a stadium, and that stadium is sending out SRT feeds, in this case to a private cloud. And within that private cloud, we have all these services running. For simplicity and for the fact that RTMP works with everything, in the setup I'm thinking of, we're using a lot of local RTMP there on the network because it's really simple. However, WebRTC previews are being generated. So as soon as the SRT, and the SRT is delayed, and it's delayed so that we have reliability. We have retransmits and reliability. So as soon as it hits that entry point, immediately a lower quality, low latency preview gets generated and sent out to a multi-viewer that a remote graphics operator is watching. And they're triggering different things to happen based on that low res. And then the control goes back into the cloud, and that's very low data. And usually we don't have bandwidth issues at all for the control. It's very similar to what Mike has talked about in the past. And then that control gets executed, and then all the compositing happens, the encoding happens, it gets shipped out the door with SRT again. That also has several seconds of delay because the internet is a jungle, right? And it gets out to the distributor in that case. So this is an example of how WebRTC is being used for production. So in some cases, in the remote contributor, the remote guest case, WebRTC is actually used for the video that goes on air. In other cases, WebRTC is used as part of the overall workflow that enables interactivity while being remote. Okay, so any questions on any of this before we dive into playing around with web? So we're going to play around with WebRTC a little bit here.
Did you look at MOQ yet? Media over quick?
Oh yeah, I have looked at that. Yes, very early days for media over quick. Quick is pretty cool too. So for those of you who may not be aware, HTTP 3 sits on top of quick. Quick sits on top of DTLS, and so it is a HTTP3 is UDP, which I find really cool because UDP traffic is not treated with much respect in certain parts of the internet, and so as HTTP3 switches to be UDP, all of a sudden UDP becomes a first-class citizen, and Chrome defaults, by the way, to HTTP3 whenever possible. And so quick. There's other cool bindings. There's actually SRT bindings over quick that are, draft. There's media over quick. We had that talk last time. Really cool. Any other questions just about WebRTC and workflow and things like that?
So at the opposite side of the spectrum, have you heard about WebRTS, which is from CBlue, and it's WebRTC over TCP?
Oh, yeah. That's interesting. Well, there is a turn profile for TCP, and so a lot of WebRTC systems fall back to WebRTC over TCP.
Yeah. So they have a proprietary way of doing WebRTC over TCP. I think it's interesting because it solves a lot of problems.
Yeah, very cool.
But it's proprietary, so it's not.
Okay, so WebRTC. So like I mentioned during COVID, I became enamored with WebRTC. I found myself with some more time on it. After the panic of switching everything to the cloud and the sleepless nights that came along with that for all the esports production I was working on at the time, I found myself a little extra time to play around. And I had clients who were all complaining about connectivity, and so I learned a lot about WebRTC, and I thought I would make a product for playing around with WebRTC. So it started as a tech experiment turned product. That's really where this came from. And so I had this crazy idea, right? Like, what if we could get beautiful audio and video in real time from anywhere? Not just from venues with carefully groomed internet connections, right? But from people's houses, from cell phones, over LTE connections, and so on and so forth. And so then my next crazy idea was, what if we go all in on the browser? Why the browser? Because apps are a thing, right? There's like Lyrics, Broadcaster, and it does a whole bunch. Soft Vellum makes that, does a whole bunch of contribution protocols. So you just make an app. Why do we care about a web browser? Well, web browsers are everywhere, right? And so really, I liked the idea of web browsers because they're already installed. Everyone here has a web browser, right? In some cases, you have multiple web browsers. Every single device we're interacting with here has a web browser, or maybe even a Chromium embedded as a web browser. And so you can reuse existing devices. You don't have to buy new devices. You don't have to provision new devices. They're great at encoding. A lot of web browser implementations, Chrome, use hardware accelerated encoding. And they're great at playout. Chromium has FFmpeg kind of as its overall media engine. So if FFmpeg can do it, Chromium usually can do it. And they're adaptive. And so if you really want to get it from anywhere, right, then you need to get rid of special equipment, get rid of special network settings, get rid of all that. And you have to be able to go back to attacking these barriers of distance, connecting at all, good quality video, delay, ubiquity, cost. There's things that do this really well, but they're not ubiquitous and they're expensive, right? And so I thought, well, what if we try to do that? Okay, so I created something called Hypersignal. So here, I will do a brief demo. 1 second. Oh yeah, live demo. Yeah, the question was, is it a live demo? Yes, it is. And if not, the talk doesn't hinge on it, but we've tested as thoroughly as possible in a few minutes, actually a few hours, but still. Okay, so what is Hypersignal? So Hypersignal is just a way to, let's say our web browser, imagine if you will, and I probably need to wake up these computers, so let's wake them up again. Hold on 1 second. Probably once my face. Okay, good. Okay, so you can see there's not a lot to see yet on the computers. We have an iPad web browser. We have a Chrome web browser, and then back here to our dashboard. So what if we pretend, if you will, that Chrome is a high-performance video and audio encoder, and Chrome is a high-performance video and audio decoder. So what if we say, hey, let's make a high-quality video encoding and decoding implementation around that, just sitting on top of Chrome. And hey, maybe it will work on Firefox and Safari too, because there's a WebKit origin and there's a lot of code that's shared between those. So we took that crazy idea and we created Hypersignal, where you have a web browser as your encoder, a web browser as your decoder, and then you can start routing things in an ad hoc way. Because guess what? WebRTC is really good at setting up and establishing sessions in some of the worst network conditions that exist. So this is the dashboard that you see. And what I have here is I have a contributor, and this is a web browser that's running that's encoding. And then I have some of these outputs on the studio side, and these are web browsers that are running as decoders. And let's see if so let me show you from the contributor's point of view. We go here, and let's see if we can. I think something's in use. Let's switch to this one. See if it works. Camera or mic? Oh, that's in use. Let's just go to microphone array. How about that? And then let's go back here. Well, when in doubt, we're going to reload. Already open. Okay, so we're going to not do that, I guess. So I've set up another one. So then you launch the encoder side. So I have an encoder here. We have our friend, Buck. Since every video demonstration has to have Big Buck Bunny, we have our friend Big Buck Bunny here standing by. And then over here, we launch a, let's see. We launch a decoder. And so what's fun is this stuff is just a URL. Right? You can see this is just a URL. So you load, oh yeah, sorry. You load the decoder, it's just a URL. Okay, so let me switch over to, hold on. We're gonna go here. So we're gonna switch here. So this is a mic stand. Okay, awesome. Okay, that's good. Perfect. Awesome. Okay, perfect. So the first thing I'm going to do, sadly, is take the mic out of this because I got to walk over there. But I will hit escape. So you can see this is a web browser, right? Web browser. And then you full screen it. And now you have a decoder. And so what we can do is we have the encoder running, And then we go here and we say, hey, let's go back here, and in the dashboard, in our little master control dashboard, we're going to go, okay, let's send this feed to the studio output. And let's go here and look at the studio output. And there it is. So you can, those of you in the room can see here on the computer, it's playing out, right? And you can also see the quality of the internet connection we have here is not amazing, right? So this is even better, because if we want to get video from anywhere to anywhere, we have to deal with places like the Lucky Labrador with less than amazing internet quality. So this is actually a great part of the demo, right? So if we go back here to the dashboard, so this is playing, you'll see that continue to play on the screen, but we can go here, and this is where you can start to see what WebRTC lets you do, which is kind of fun. So way down here at the bottom, and it might be really small type, and so, but it has live stats of what this feed is doing. And right now, we're getting this video through with 0.3 megabit, 0.3 megabit. And we're getting the audio through with 32 kilobit, right? So, but we're also getting it sent directly over this pretty hostile connection. So let's go here. Let's send this over here to the iPad. So now let's go here and let's look. Boom, there it is on the iPad. So we just dynamically rerouted the video, and that's how fast the session negotiation happens with WebRTC in a terrible network, right? In a terrible network. And it's a totally different platform. This is Safari, the other one's Chrome. I brought it, and it's in my bag, and I meant to get it out, but I have a little Android stick that has a HDMI on it. I'll show you, if you come up, I'll show you afterwards. You just plug, it literally is designed to plug into the back of a TV and be powered off of USB. Guess what? That has Chrome on it too. That does WebRTC. You can just start sending the video over there too, which is kind of amazing. So if you come back here and we look here at Buck, and we can go, okay, well now we're getting 0.9 megabits. Yes, right? And it's telling me that it's being sent over UDP, and it's being routed directly there. I know we're on a NAT, so it punched right through that NAT to get in here. And the round trip time between the source, which, you know, spoiler, is at my house, so is 60 milliseconds, right, direct. And right here, the bit rate, it's being, the resolution it's being captured at here is at 1080p. But it's being encoded at 960 by 540, so it's dynamically resizing it down because, hey, we got 0.7 megabit now, right? We do not have amazing internet. So what's fun is WebRTC lets you squeeze, right? I can squeeze this down to 0.5 megabit if I want, right? And I can give it a threshold of 5, but it's going to use that bandwidth estimation to be able to do that. Because WebRTC supports a bunch of different codecs, we can go, what if we encoded this at H.264? And let's go see what that looks like. Let's let it renegotiate, see if it fires up. And there it is at H.264, because you can just protocol shift, right? So it's our favorite friend, Big Buck Bunny, right? Mandatory. And, you know, let's go back and let's, here, I'm going to switch here to the studio output, and let's go here and I'm going to send it to studio. And there it is. Boom, H.264. And does it look any better than VP8? VP8's a default? I don't know. We could even do AV1. I don't think this is going to work out real well because AV1 software encoders are not amazing right now. They're getting better, but let's see what happens. Okay, here we are, AV1, right? Because Chrome supports AV1. So all of these codecs are codecs that Chrome already supports, right? And they're just, you can just start using them, right? Because you're controlling both endpoints. It's like the classic thing in transmission where you use the same encoder and decoder on both ends. And so we can switch, and now we're doing AV1. So let's look at back here. We're back at 1 megabit. Well, 1 megabit of AV1 looks, wrong source, looks pretty good, you know. This projector doesn't do anything justice when it comes to color fidelity, but hey, we're gonna go with what we got. Yeah. Yeah, the whites are struggling, right? for those of you in the room. But there you go, right? And so, well, okay. What if we say, let's take this AV1, let's force it to go through a turn server, and let's send it through the East Coast. Let's see what happens here. So we're going to wait for it to renegotiate. So, hey, look, we got video again. And if we go down here, now our round trip time is 166 milliseconds, right? Because we dynamically rerouted it through a turn server. Oh, wrong output. Let's try that again. Dynamically rerouted it through a turn server, right? What if we say, let's send it through London? Why not, right? Now we got 341 milliseconds. So we're literally sending it to London and back in 341 milliseconds. That's low enough latency that you feel like you're having a conversation still, right? And so that's not because I'm a genius programmer so much as it is WebRTC enabling that, right? And so what's fun, at least what's fun with this tool, is it allows you to take WebRTC point-to-point connections and figure out what the settings are that are going to work for that environment. And here with a 0.5 megabit of AV1, we're doing pretty well, you know? It's certainly good enough for an interview. We don't have audio. We're not doing the audio part of this, but the audio is way easier because it's way less bandwidth. And if you recall at our last meetup, for those of you who are here, we ended up switching to audio only for a while because the internet was having so much trouble. It's like, no problem. We can just go here and we can just switch to audio. In this case, we're not hearing it, but oh, I muted it and then unmuted it too quickly. Blinded it. So anyway, so that gives you an idea of what is possible with WebRTC. I would love to open it up for some questions. I'm gonna set this back to not going through London, but you know, yeah. Any questions? Also, I will say this: if you want to connect with me on LinkedIn, scan this code right here, and you can connect with me on LinkedIn. So if you're looking for me on the internet, you can find me there. And I'd love to connect with you on LinkedIn. But I would like to open it up for some questions, if there are any more questions.
Have you ever done DRM or encryption over WebRTC?
So WebRTC, the whole stream is encrypted, and because it's point-to-point, it's session-based,
yeah,
right?
It's
so
well,
yeah,
DTLS. It's not really
right. So it's session encryption, not media. Yeah, not pre-encrypted. And so because it's all session-based, you secure the session, so you authenticate the session. So the session can't start, and you can't snoop on the content because the session itself is encrypted. But you don't get any. It doesn't scale out real well. Just ask the folks at Millicast, and I think actually.
Yeah, there are solutions.
Yeah.
EasyDRM and Cast Labs, they can do.
Yeah,
encryption
but I
over
haven't done it.
WebRTC on
Yeah.
Minicast.
I haven't done it. None of the projects I've worked on needed anything more than stream encryption. It's a great question. Any other questions?
Do you think that WebRTC will survive Media over Quick? Or do you think Media over Quick is going to take over everything?
I personally believe Quick will continue to take over everything once it really gets standard and worked out, because WebRTC is going to be around for a long time because it's there and it works. But as browsers move to supporting Quick, and there's web codecs right? And web transport, which is web transport's like a thin layer over quick, and web codecs, you can begin to send some of your own elementary streams over your own quick too. So between media over quick and web codecs and web transport, you're going to see more and more applications take advantage of that. But it's going to take a while. WebRTC has been around for a long time.
Other questions? Guys? Mike, you have a question. I cannot believe you don't have a question. Just
Mike knows too much about WebRTC already.
So you are, since I have to ask some question, I'll
Yeah.
ask the biggest problem we ran into in WebRTC is browsers changing their implementations. And do you track that? Do you, like, you didn't mention Firefox at all?
Oh, yeah.
So what happens if, do you like keep monitoring releases of browsers like Firefox to see if it's going to cause you problems?
Yes. Yeah. So yes to all of the above. Yes, we track it, and yes, we monitor browsers. So Chrome, for example, Chrome just had an interesting regression in their jitter buffer, specifically for H.264. And so if the packets are arriving out of order, if you have packet loss, and the WebRTC stream is H.264, it's very stuttery right now. So for live production, we often just tell people, hey, use Firefox or use Chrome.
Yeah, so for me, that was the most frustrating part of WebRTC, is you're basically taking these things that are really, really important, like for viewing your media, and you're throwing them into, somebody else is responsible for that code.
Right.
And so I guess that I was just wondering if that situation has gotten any better.
Yeah, I'm on the WebRTC mailing list, and the maintainers have said in more or less words that it is what it is. The future really is web codecs, web transport, and quick, right? Web codecs, web transport is sort of you have total control. Quick, media over quick, once again, it's standard, but it's a little more flexible. But it's an emerging standard, so who knows, right? Yeah, there's other crazy things that people do too, like take H.264 and AAC audio packets and send them out over WebSockets. So there's something called SLDP, which Soft Vellum, the makers of Nimble, have pioneered. So people do that. Zoom and Google Hangouts both play that trick sometimes, where they're doing their own codecs and sending it out over WebSockets and crazy stuff like this, right?
So that reminds me, you didn't mention the data channel of WebRTC, and that's actually, I believe, somebody could tell me if I'm wrong, but I believe that's like, for example, how Zoom used to.
Yeah, they also do that too, yes.
Yes. It's like very important, I think.
Yeah, so Zoom has their browser player, right, their browser client. And they switched, I believe they were using WebSockets before. I'm not a Zoom engineer, so this is just, what I read. And then they switched to using data channel WebRTC. And so data channel, you can pass any arbitrary. And so once again, people are using the web-based, the media APIs, the web media APIs to encode things, packetize them, shove them out over WebRTC, and then reassemble them and play them out using blob and tricks like that. The HLS.js player plays all these tricks too. It's a topic for another day, but yeah. Great questions.
Thank you very much.
You're welcome.